didn't implement the BFS last time, so we asked you guys to do it. So now I'm going to implement the BFS real quick. I'm not going to, we already kind of explained that, how we're going to do it. And you either queue or recursively. So here I'm going to use the queue. And I have it already, so I'm not going to explain it because this is your job to write this code. I'm just going to put it here. You can, again, as I said, you can do that in a recursive way too. Okay. Oh, BFS. Like, what is going on here? The queue that I used, here I use the basically the queue of the Java library. So Java util queue, I use that. So that's also a good example to see how that is implemented. Also the linked list that it's going to, because the queue is implemented with linked list in the Java library. So I'm going to use that. I use that one basically. So as you can see, based on what we explained, it started from the root and you keep checking adding it to the queue, and as it go over the element of the queue to making sure it's not empty, it's going to add all the children's from left to the right into this queue. And so this is a while we keep going all the way to the queue. And we also added like the fact that if it's empty, we're not even go continue doing that. So now I'll print this because my print method, so print now is using this. So if it's showing me the same order, I know the level by level is the same. So starting from roots, the 10, 40 are in the same level, then 60, 30, 80, and then 27 and 50. I guess I missed the 14 here, so I need to, right after 27, I need to add the 14, so you can make exactly the same example of the slides that we just saw. Now I'm going to print it again, and yes, sure. So that's this has to be here. So that is showing that we implement this correctly. Now, what I want to do is just to deleting elements. So I know that 20 is the root, and if I remove 20, it's going to be the case 2, right? Because it does have a left children, and also based on the slide example, the 16 is going to be the most right child of it. So let's see if this is going to work the way we expected it to work, and then we print out that, see if it's so we're going to remove the 20, and then we're going to print it again using the level by level. So now 16 become a root. Perfect. And 10 and 14 on the same level. Then 14, 30, and 80 are in the same level. Perfect. And then 27 and 50 are in the last level. So we did remove that. So it's case 2. Now I'm going to remove 16 again. So 16 is the root. It does have a left child, which is a 10, right? And so you can check the slide page 41. That's the example that I'm trying to basically implement. And now when I remove that from this list, then it's going to be, I expect to see that basically the 14 is going to become the root, because 10 is the basically left child, and the only right child of 10 is 14, so that's going to be the rightmost. So let's run this, and if this if I run that, the 14, perfect, 14 is the root. 10 is going to go into our level with 40, and then we have 30 and 80, and then also 27 and 50. So now if I remove the root again, which is 14 in this case, right? If I root this again, then the only thing in the left is going to be the 10, right? So 10, although it's in the left side of 14, which is the root, but also it's the only one. So that's also considered the most right node, so the rightmost node. So 10 become the roots now immediately after I remove it. So that's the case that we just described here, right? That's going to be this case that then suddenly we don't have any other children in the left side, and the only thing we have is the left child of the current that they're trying to remove. And so the left child itself is leaf. So then when you're trying to find the parent, is going to be the parent that left. Sorry, where I should be here. The right parent left, rightmost left is going to be the basically the one. So here, in the example of 10, the rightmost left also of 10 is going to become null, right? So that makes the parents to be null, and that makes sense because 10 become root, and 10 doesn't have any parent, so the parent of it is null, and that's basically what we expect to see as well. So we run it again now, and you should see that the 10 should print the very first one, right? Because the 10 is now the root. And the 40 is the next level, then 30 and 80 are the next level, and so on. So we completely remove everything in the left side of this tree. And they were all case 2, different case 2s. But now I'm going to remove 10 too. So if I remove 10 now, 10 is the root, and there is no children in the left side of it. So it's become case 1. So this is a case 2. Example of a case 2. This is a case 2 again, similar to that. This is a case 2, but in a situation that we don't have no right child for the current that left, right? We didn't have any right child. This is become completely the case 1 because we're trying to remove the root, and root doesn't have any left children, and everything has its right children. So the node right after the root is 40. So when I delete that, I expect 40 to become the root now. So I remove that and see 40 now is the root, and 10 is removed. The tree is empty. It keeps going to print out somehow. I will update my code in binary. I'm just going to remove it. I don't know why it printed it. I fix it later. So now the 40 is going to be the root. And if you keep going, right? So if I remove now 40 is going to be case 2 again if I remove it. It has the left children 30, but the 30 doesn't have any right children. So if we're trying to remove that, 30 is going to become the root, and the 27 is going to become the left child. So it's going to still be case. So we can keep going until the 3 are getting completely empty. So I'm also going to emphasize on it. This is the example for the chapter 25, slide number 41. So that's the tree that we implemented. So in case you want to just do it yourself as well, just to kind of visualize it for yourself that what we're really doing, that is going to be on that slide. So we tested our delete method too, and it's working perfectly fine. So the next, so basically assignment for next week is that to implement your own basically delete method and tested it. Okay, so I'm going to stop this video here. And next video that you're going to see is going to be talking about the heap data structure. So that's going to be very quick as well, because we already know tree. We already see one type of tree, which is a binary search tree. And now we're going to specifically talk about another type of tree, which is going to be the heap. And so we're going to talk about that. Okay, so bye for now. And talk to you soon.